Hello, this is Chen, Chief Executive from Futurewei Technologies. Today I'm going to present beyond zoned namespaces, the ZNSNLOG bridging the semantic gap. By semantic gap, let's take a look at what are running on the storage devices and how devices are used. Here, I presented the most widely used big data frameworks. We have the popular Hadoop, Storm, Hive, and Spark. Also the promising ones like Flink and Heron. If we go down the software stack, we can see they are supporting database or data stores like HBase, Cassandra, or single node ones like RocksDB and LevelDB. For the distributed ones, the underlying distributed storage could be Hadoop HDFS, Kafka, or even newer Apache Bookkeeper. Those are all backed by a native file system like ext4, XFS, BetterFS, or ZFS, those journaling file systems. Lastly, the file system operates on block devices like NVMe drives with or without ZNS, or NVMe drives over Fabric, or legacy SATA and SAS drives. Let's take the popular RocksDB and dive into the details. I'm going to focus on the write flow. For every write, RocksDB first persists the data onto the write ahead log, then store it in the volatile mem table. When the mem table becomes full, it will become the immutable mem table, waiting to be flushed onto persistent media. The flushed data will be stored in SSD file or static sorted table. Those files are referred as L0. Each file is around 10 megabytes also, covering the whole key range. When there are enough L0 files, RocksDB will merge sort those files into multiple L1 SSD files, each file covering a particular key range. Those L1 files is around 100 megabytes also. The merge sort process is called compaction. The compaction process will happen for the rest of the levels, and some files can be several gigabytes in size. As you can see here, the write ahead log is a log, and all the SSD files are logs as well, and those files vary in size. Now, let's take a look at Kafka. Kafka is a distributed streaming platform. Kafka cluster allows the producer to publish or write, and consumer to subscribe or read stream of events. The events are stored persistently and reliably by the storage layer called brokers. The stream of events are organized into block topics. Let's take a topic as an example, showing on the right-hand side. Let's say I have a stream called my topic. It's replicated onto 3 brokers, broker 0, broker 1, broker 2. Each broker will partition the topic onto subtopics like my topic 0, my topic 1. Those are typically implemented using directories. Each partition is a log of events. The log of events is further sliced into segments. Those are implemented using files. For each partition, Kafka will only append at the end of the last segment. Once the oldest segment is no longer needed, it will be deleted by the system. Anything in between are ready for consumption. We can also see here that partition is a log organized into segments, which are also logs. When we append to the partition, we create segments and append to the segments. When we truncate a partition, we delete the oldest segment. Also, HDFS is write once with append and truncate capabilities, match very much look alike, log alike. Let's also take a look at Apache Bookkeeper, a high performance and low latency storage service. Apache Bookkeeper is used extensively in Twitter. It's also the storage engine of Pulsar, a cloud messaging service. Bookkeeper is used in Salesforce distributed store and other places. Bookkeeper abstracts the data to be stored on a distributed log. In fact, Bookkeeper's original name before graduation was distributed log. The log consists of ledgers. A ledger consists of segments. Here, a segment can be large or small. A record is always added at the tail of the log. Once a ledger is full or closed due to change of ownership, it's immutable. New writes will happen on a new ledger. What separates Bookkeeper and Kafka is Apache Bookkeeper has stateless serving, where the write proxy and read proxy can be spawned quickly to respond to heavier loads. The actual data and the state is stored in the entity called a bookie. A quorum bookie is required to acknowledge a write and certain reads. So when the writer add an entry, this last add pushed position is updated. This is a consistent view among writers. When the quorum of bookie acknowledge the write, this last add committed, confirmed, is updated. This is the consistent view among readers. To change the ownership to a new writer, the new writer will fence the in-progress segment on the participating bookies. The bookies, in turn, will reject new writes from the old writer. Realizing its write are rejected, the old writer is forced to finish the outstanding writes onto the new segment. Then the new writer can append new writes. Inside a bookie, with default DB ledger storage, each new record is first written onto the write-ahead log as well as write cache. The write cache is periodically flushed to log entry file. The mapping of ledger ID and entry ID to this log entry file and offset is stored inside the RocksDB ledger index. As you can see here, it's all logs. In addition to a big distributed log, the concept of smaller individual logs are also used here. Moreover, the concept of last add pushed and last add confirmed, those positions are fancier names for collective write pointers of each log. All those are data plan engines. Let's take a look at a control plan engine. Facebook's Delos is a replicate storage engine for control plan. It is similar to the Bookkeeper in the sense that it uses smaller logs called loglets to construct virtual log, which support 3 operations: append, which store a payload in the virtual log and return a position in the log; check tail, which return the first unwritten position, and also read next, which take the position as an argument, return the first record of the set location. Individual logs also support seal function to make the loglet read-only. This is crucial for Delos' ability to switch storage engines. When multiple clients append to the same virtual log, if one loglet is sealed, the other client will not be able to append. Thus, they need to query the meta store to find the latest loglet, then append to the new one. With this mechanism, Delos can switch engine on the fly, such as from Zookeeper loglet to native loglet and back and forth without disruption to the application. I used to think log is one kind of data. Study those modern storage engines and distributed storage platforms, let me realize that the data is log. This already happened. We can try to find the common semantics. So the common traits number one, all implementations are log-based. They all use append to persist income data. Why? Obviously, for streaming processing, data comes in stream. Thus, naturally, the append semantics. Also, sequential write is the faster way to write for both HDD and SSD. And it's going to be the fastest method to write for persistent memory as well. In a distributed environment, log is the simplest and the fastest to reach consensus. So that's the consistency. In the case of failure, the log is also the easiest way to recover. So that's the reason that all those systems are using writes, append semantics. Common traits number two, all implementation are split into smaller pieces. You can call it segment, you can call it SST, you can call it ledger. Each smaller piece, once closed or sealed in Delos, are immutable. This helps the consistency as well as the takeover. Number three, when we delete segment, each segment is deleted as a whole. Number four, sometimes we always need to find a way to know where to write next. So this is the tail function, either individually or collectively. Number five, by using fence or seal, we can make active segment read-only, thus gracefully handle the takeovers. See where I'm going now, right? Before we move further, let's think about what is supporting those logs on individual nodes. It's a native file system. Let me ask you this question. Can native file system efficiently support those? Definitely they can support. It's working on native file system now. But the keyword here is efficient, defined as achieving maximum productivity with minimum wasted effort or expense. Let's find out if native file system is up to task. This is a paper published in SOSP 2019, titled File System Unfit as Distributed Storage Backends, Lessons from 10 Years of Ceph Evolution. Ceph started with EBOFS, extends and B-tree-based object file system. Then in 2019, they switched to BetterFS and hooked into file system internals, trying to improve the performance. Then they used user space write-ahead log on XFS in 2012. In 2015, they experimented with RocksDB on journal file system, and that did not go into production. In 2017, they switched to BlueStore. Let's take a look at the BlueStore. In Ceph, clients talk to multiple storage nodes. Each storage node is attached with multiple storage devices. Each device is served by one instance of OSD. With the BlueStore, the OSD works directly on raw devices, bypassing the file system. The metadata is managed by RocksDB. The RocksDB uses logs for store abstractions. That's quite different than the raw storage device, which provide the block interface. What do they do then? This is where the BlueFS kicks in. The BlueFS operates in user space, turn a raw storage device into a log interface. Then everything will run on raw devices, bypassing the kernel file system. They claim that twice the performance improvement, and the most impressive part is they stabilize the whole code base in 2 years, not the usual 10 years if it's a full-fledged file system, due to the simplicity and limited semantics. So the key takeaway here is modern database and distributed storage are using log-structured approach to manage data, including metadata. Here, the log approach means append only, immutable, and delete as a whole. And the logs vary in size from several megabytes to hundreds of gigabytes. Additionally, they use very limited semantics. Most existing data processing frameworks are still using native file system, which is demonstrated to be unfit. The reasons are native file system is slow in read, modify, write. There are double writes issue when you use a write-ahead log on top of a journaling file system. Also, a native file system is slow to adopt new hardware like Zoned Namespace, which already supports some of the common operations like append, like tail, like sale functions. So this feels like both the application and hardware aligned to a common limited semantics, but the file system in the middle, being backward compatible, is demanding a lot more semantics, make it cumbersome and slow. Speaking of zoned namespace, let's review what it is. A zoned namespace or ZNS device will divide the whole LBA range into multiple zones. Each is fixed sized, normally several hundred of megabytes. Within each zone, we can only write sequentially, namely write where the right pointer is. When the zone is full or zone is closed, it will be immutable until the right pointer is reset. We normally map this reset right pointer action onto the SSD's block erase command, essentially delete the whole zone. We can also by setting the zone mapping configuration, the zone size can be large or small, depending on the number of flash dies it spans. Also, take a look at the zone state machine. We have empty state zone, ZSE. Full state, ZSF. We also have ZS open state, which is implicit open and explicit open. We also have closed state, which is ZSC. Most important one, in my view, is the read-only state, ZSRO, which is perfect for operation like seal. There's also a command called append, which enables multiple outstanding updates to the same zone, greatly improve the write bandwidth. The caveat is that it's a nameless write, meaning the append doesn't specify the address. Instead, the written address is returned by the device. As we can see here, zoned namespace improved performance, increase the bandwidth while reducing the write amplification, improve the tail latency due to zone isolation and reduced garbage collection. Overall, zoned namespace reduced TCO by enabling less over-provisioning, less DRAM, less write amplification, and enabled adoption of QRC media. It's all very good, but can we do more? Can we do better? Can we directly map application log onto zones, even the logs for distributed systems? Let's compare the application logs and the zones. Both append only, both are mutable until delete. For the seal ability, which is required for handling takeovers, ZNS already have this read-only state, ZSRO. And to check the tail, which is required for synchronizing writers, we can query each zone's current write pointer. As you can see here, ZNS already have most of properties to map application logs, but there are a couple of missing pieces. The application log has a variable name, while each zone has fixed size. And also the application log update may not align with sectors, but the update in zone has to be sector aligned. Additionally, application log is identified by directory, file name, or object ID, while the zone uses ZSLBA, which means we need a file system or a metadata server to map the name to LBA. Can we map application onto current zone in the current zone namespace? There's two possible approaches. We can map log into zones, and multiple log into a zone, one log span multiple zones. The downside of this approach is we have an internal fragmentation. And if we're sharing a zone, it will incur garbage collection. And we still need a naming service to map name to an LBA. Another approach is to extend the zone to support application logs with the following: variable size zones, byte level append, and naming. We call this ZNS named log extension, or ZNSNLOG for short. Essentially, we extend the zone concept to be named, byte append-able, variable size, linear space. By named, we allow each zone to be named and map the name to a unique zone ID. Also, each zone can span different number of flash dies. For a small size zone, like zone ID 3, we can use only 2 dies. While for a large size zone, for example, the zone ID 2, we probably need to use all the flash dies. For byte level append, let's look at an example. We have 4 appends. Each is smaller than a sector. We can stage all the partial appends in a buffer until the buffer contains enough data to fill a sector. At such point, we can flush the buffer to actual NAND. Any questions, please ask on the Slack channel. I will answer there. Let's dive into the details for each aspect. Byte level write seems to be intimidating at first, but byte level append can be implemented efficiently. When the queue depth is 1, the nameless writes or appends can be implemented using simple staging buffer, power protected. Append command is acknowledged once it's accepted into the buffer. When the buffer is full, data are flushed onto NAND media. The same mechanism works for normal writes, since we only accept sequential writes. With queue depth is 1, normal writes is just append operation with the address. With queue depth is more than 1, for appends, the simple stage buffer still works, as the drive is free to reorder all the outstanding appends and put them in the buffer in any order. It's going to be tricky for normal writes. The drive need to order or reorder the writes in the designated order indicating by the write address, and only acknowledge the writes that are consecutive in addresses, leaving no holes in between. In other words, the acknowledgement of writes will hold for missing write. For example, here we have a missing write number 3. The act on 4 is on hold due to the missing 3. Even though complicated, this mechanism has added benefits in a distributed environment. As distributed log need to maintain the same order among replicas, the write address is perfect for ordering. With this feature, the partial sector read modify write can be eliminated, thus reduce the bandwidth requirement for partial sector appends. Those appends are perfect for write ahead log up to several folds of reduction in WAL writes of RocksDB. These savings seem to be trivial in single device systems, but in a network environment, where the network bandwidth is likely to be the bottleneck, the benefit can be significant. Now onto variable size zones. One key advantage of adopting ZNS is the possibility to achieve write amplification of 1.0, the lowest possible. Why ZNS can achieve write amplification at 1? Because we always delete a zone as a whole. There's no internal copy forward or the garbage collection. Thus, the device write amplification is 1. But can we keep write amplification at 1 when segment is smaller than a zone? Well, the device amplification is still going to be 1, but we need to copy forward all the valid segment to other zones before we recycle a zone. So the overall write amplification is going to be bigger. We can mitigate the issue by grouping the segment to be deleted together into the same zone and pray that those zones indeed expire together. There's also a possibility to reconfigure the device into smaller zone sizes. The issue with smaller zone size is a dilemma here. Each zone's write throughput is largely determined by the number of dies it spans. So for a zone which spans only 1 die, the write throughput could be as little as 2% of the total write throughput. That's the reason we propose variable size zones. A zone can be either span as few as 1 die or as many as all dies, or anywhere in between. The user can demand a zone with different performance characteristics. Once we introduce variable size zones, it's no longer possible to name each zone using their ZSLBA. But we think about it positively, we free the zone ID from its LBA binding. What we can do here is to name zones with generic names, or even using file names or object name. This has added benefits. We can bypass the file system naming service. We can directly find the log on the device without the file system involvement. And we can port such concept into Fabric setting as well. In a distributed environment, we can choose a global name as a name for zones. This will eliminate the mapping, which map global names to a storage device and its local name. The client can directly send global name to sharded storage devices. Doing so reduced remote access latency, as well as the work performed by the metadata server. There's more scalability. Let's rewind to check if ZNSNLOG can support application log better. Yes, we can support both sector level append as well as byte level append. Great for write ahead log. Yes, we can have multiple size zones, greatly reduced internal fragmentation, and the balance write throughput. Even though we have to switch to a more complicated naming scheme, naming zones with generic names also have added benefits. First, it frees us from file system mapping, and it, in a distributed environment, it makes metadata server simpler by removing the global name to device file name mapping. Let's take a look at how to port RocksDB over ZNSNLOG. First, the write ahead log. We avoid read modify write by leveraging the byte level append. Thus improve the write ahead log write throughput. And let's say we have 65,000 small zones and 4,000 medium zones and 512 large zones. We can map L0 and L1 SSD files onto small zones, L2 SSD file onto medium zones, and the very large SSD files onto larger zones. Because there's no zone sharing, we can reduce the overall write amplification. Lastly, we can directly use the name like L0 F2M 010 SST or L2 X2Z 005 SST as known names, eliminating the file system to LBA mapping from native file system, making the mapping fast and robust. So further, ZNSNLOG enables more NDP. For example, it allows transparent compaction of the zones, meaning we can maintain the original logical offset within a zone. We all know that larger file size means better compression ratio. Now the drive can compress the whole zone, not the individual blocks, which the size is artificially defined by the file system. Also, we can offload some of the RocksDB operations like compaction of the SSD file. Because one SSD file is one named zone, we don't need native file system indirection. And compaction is self-contained with the device. We can leverage SSD huge internal bandwidth. We can also search multiple SSD files on the device or even wildcard search, which is not supported by the current RocksDB's normal Bloom filter or the prefix Bloom filter. For Kafka, we can also offload the matching operations. In a distributed environment, the ZNSNLOG really shines. Let's take a replicate storage, for example. Let's say you want to replicate logs onto multiple devices over Fabric. Since the write addresses dictate the ordering, you can use the addresses to keep all the writes in same order, regardless how many outstanding writes are there and how messy the network reorder the writes. With naming capability, where the log can be directly named to use global file names or global object name, you can name each copy of a replicated log as log.r1, log.r2, log.r3, and so on. Or we can use erasure encoding to store distributed log. Then in that case, the log name can be log.1 out of 3, 2 out of 3, 3 out of 3, P out of 3, and Q out of 3 for 3+2 coding scheme. This is also applicable to persistent memory, as we know that persistent memory is native byte addressable. So it's byte appendable. Also, the memory allocator will dictate the size of allocated memory region. That means if we just add a naming service, we can implement the ZNSNLOG on persistent memory. This way, we can provide a same semantics on both persistent memory and SSD. We do have working prototype provided by Huawei. The prototype is semantically equivalent to ZNSNLOG, but built with a full custom interface. The prototypes are available to partners now using remote access. We plan to propose ZNSNLOG extension to NVMe Express when it's validated by several partners and is mature enough. Here is our call for collaborations. Currently, Futurewei is sponsoring 2 efforts, adding ZNSNLOG support to FEMU, a flash device emulator. Second, port LevelDB RocksDB over to ZNSNLOG. We need partners on improving the specification, alternative implementation and the design, also port more log-based application like Kafka, Bookkeeper, and so on. Please contact me or my colleague Nielsen at the email address shown here. So in conclusion, ZNSNLOG can bridge the semantical gap between application and SSD, which traditionally was blurred by file system. By providing the 3 features, naming, byte append-able, and variable size zones. ZNSNLOG enables less write application, more log write performance, and provide more functionality for distributed systems. ZNSNLOG also lower the technical barrier for near data processing. Lastly, the ZNSNLOG concept is applicable to persistent memory. We're welcoming collaborations. Thank you for your time.